The morning of July 23rd, 1944, a British anti-aircraft battery positioned along the coastal strip near Dover. Gunner Sergeant Malcolm Price watched through the morning haze as yet another V-1 flying bomb approached from across the English Channel, its distinctive pulse jet engine creating the mechanical buzz that had given it the nickname Doodlebug. Price had been firing at these terror weapons for 6 weeks now. His battery, equipped with 3.7-inch guns, had expended thousands of rounds. By his rough calculation, they'd destroyed perhaps 1 in every 10 V-1 second that entered their firing zone. The mathematics were brutal, and the consequences even worse. Every missile that slipped through meant another explosion somewhere in London, another neighbourhood destroyed, more civilians dead. This morning was different. 3 days earlier, his battery had received a shipment of new ammunition. The shells looked identical to standard high-explosive rounds, but the nose fuses bore unfamiliar markings and came with strict handling instructions. His commanding officer had been deliberately vague about what made them special, saying only that they were American-made and that the entire operation was classified. Price tracked the V-1 through his sight picture. The flying bomb was crossing at roughly 400 miles per hour, at an altitude of about 2,000 feet. He fired. The shell left the barrel at 2,800 feet per second. 4 seconds later, without striking anything visible, the shell exploded in midair, approximately 50 feet from the V-1. The blast wave and shrapnel tore through the flying bomb's thin aluminum skin. The pulse jet engine stuttered and died. The V-1 pitched forward and plunged into the English Channel. Price stared at the splash, trying to comprehend what he'd just witnessed. He hadn't hit the target. The shell had detonated while still separated from the V-1 by several dozen feet of empty air. Yet the weapon had been destroyed as effectively as if he'd scored a direct hit. Over the next 4 hours, his battery engaged 12 more V-1 second. They destroyed 9. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The transformation in effectiveness was so dramatic that Price assumed some error had occurred in the count. But the pattern held. Day after day, using these mysterious new shells, British anti-aircraft batteries that had struggled to down even 20% of incoming V-1 second were suddenly destroying 70, 80, sometimes more than 80%. What Price didn't know, what almost no one in the British military knew, was that he was firing what would later be recognized as one of the most revolutionary weapons of the Second World War. Each of those innocuous-looking nose fuses contained a complete miniature radio transmitter and receiver, a battery that activated, through centrifugal force, a complex electrical circuit, and 4 vacuum tubes smaller than anything previously mass-produced. The device was detecting the V-1 through reflected radio waves, and detonating automatically when it sensed the target was within lethal range. The Americans called it the VT Fuze, deliberately misleading code that supposedly stood for variable time. The British military establishment, which had been trying and failing to develop such a weapon since 1939, called it impossible. German engineers, when they eventually recovered intact examples from duds, called it the most sophisticated piece of electronics they had ever examined. And the man who'd led the team that actually made it work, a brilliant but volatile physicist named Merle Tuve, had spent 4 years being told his entire project was worthless. The story of how the proximity fuse came to destroy 90% of V-1 rockets over Britain begins not with the terror weapons themselves, but with a fundamental problem that had plagued military planners since the invention of the airplane. How do you hit something that's moving at 300 miles per hour when your projectile takes several seconds to reach it and you need to explode within a few dozen feet of a target you can't directly touch? In the early weeks of the Blitz during 1940 and 1941, British anti-aircraft gunners defending London faced a grim reality. Statistical analysis showed they were expending approximately 20,000 artillery shells for every German aircraft they managed to destroy. Some estimates ranged as high as 100,000 rounds per kill. The mathematics were simple and devastating. At that expenditure rate, Britain would run out of ammunition long before Germany ran out of aircraft. The problem wasn't the courage or skill of the gunners. British soldiers were firing some of the finest artillery pieces ever manufactured. The 3.7-inch anti-aircraft gun was mechanically superb, capable of firing at a rate of 20 rounds per minute to an altitude of over 30,000 feet. The shells themselves were precisely manufactured, filled with high explosive, and equipped with either impact fuses that detonated on contact or mechanical time fuses that could be set to explode at a predetermined altitude. Neither type of fuse worked effectively against aircraft. Impact fuses required a direct hit on a target that might be maneuvering at 300 miles per hour, presenting a cross-section only 30 or 40 feet across, at ranges exceeding 10,000 feet. The probability of actually striking such a target was vanishingly small. A shell that passed within 10 feet of a bomber, close enough that a gunner watching through binoculars might think he'd scored a hit, would sail harmlessly past and explode when it eventually struck the ground, or simply self-destructed at maximum altitude. Time fuses seemed more promising. A gunner could calculate the altitude where he wanted the shell to explode, set the mechanical timer accordingly, and fire. If his calculations were accurate, and the aircraft remained at that altitude, and the timer functioned properly, the shell would detonate near the target, and the shrapnel might inflict damage. In practice, this required getting 3 separate variables exactly right simultaneously. First, the gunner had to accurately estimate the target's current altitude, which was difficult given that aircraft were constantly climbing or descending. Second, he had to predict where the aircraft would be several seconds in the future when the shell reached that altitude. Third, the mechanical time fuse had to function with absolute precision, detonating at exactly the right moment during the shell's trajectory. Get any one of these factors wrong by even a small margin, and the shell exploded hundreds of feet from the target, accomplishing nothing except contributing to the general noise and smoke that characterized anti-aircraft fire. The result was that vast barrages of artillery, hundreds of guns firing thousands of rounds, created impressive displays, but achieved minimal actual destruction of enemy aircraft. British scientists and engineers understood the solution conceptually. What they needed was a fuse that could sense when it approached a target and detonate automatically, regardless of whether the gunner had calculated altitude correctly or whether the aircraft had maneuvered. A proximity fuse. The consensus among every nation that examined the problem was that it was theoretically possible but practically impossible given existing technology. In 1939, as war approached, British researchers at the Telecommunications Research Establishment began serious work on the problem. A team led by William Boutmont conceived of using a small Doppler radar system. The fuse would emit radio waves. When those waves struck an aircraft and reflected back, the frequency would shift due to the Doppler effect, the same phenomenon that makes a train whistle sound different as it approaches and recedes. When the reflected frequency reached a specific value, indicating the target was close, the fuse would trigger. The theory was elegant, the engineering was impossible. The smallest radio transmitters available in 1939 were roughly the size of a large suitcase and required external power sources. Even miniature vacuum tubes designed for hearing aids, the most compact electronics then manufactured, were far too large and delicate to fit inside an artillery shell nose fuse. And even if they could be miniaturized further, there was no conceivable way such delicate components could survive being fired from a gun. When an artillery shell is fired, it accelerates from 0 to roughly 2,800 feet per second in approximately 20 feet of gun barrel. This creates an acceleration force of 20,000 times Earth's gravity. Every component experiences a crushing shock equivalent to being hit with a sledgehammer, while simultaneously being spun at 25,000 revolutions per minute as the shell passes through the rifled barrel. Vacuum tubes, with their fragile glass envelopes and delicate internal filaments, would be pulverized into powder. British engineers conducted extensive testing using unrotated projectiles, essentially unguided rockets that faced much lower acceleration forces than gun-fired shells. They developed working prototypes that functioned perhaps 50% of the time under ideal conditions. For military use, this was inadequate. A weapon that fails half the time is worse than useless because it creates unpredictability in fire planning. By 1941, Britain's proximity fuse program had produced valuable research but no deployable weapon. The breakthrough, when it came, resulted from a combination of American industrial capacity, scientific brilliance, and what can only be described as institutional stubbornness bordering on insanity. In June 1940, as France fell and Britain stood alone against Nazi Germany, President Franklin Roosevelt established the National Defense Research Committee, tasked with coordinating scientific research for military applications. The committee's chairman was Vannevar Bush, a former dean of engineering at MIT, and a man with an extraordinary ability to identify which technically impossible problems might actually be solvable with sufficient resources and talent. The United States Navy immediately submitted its wish list of needed technology. At the top was a proximity fuse for anti-aircraft guns. Naval commanders, watching Japanese and German naval aviation develop, understood that aircraft were becoming the dominant threat to surface ships. The Navy's 5-inch .38 caliber gun was mechanically excellent, but without effective fuses, it was firing thousands of rounds to down single aircraft. In a sustained air attack, ships were being overwhelmed simply because they couldn't shoot down enough attackers fast enough. Bush assigned the project to Section T of the National Defense Research Committee, placing it under the direction of Merle Tuve at the Department of Terrestrial Magnetism of the Carnegie Institution in Washington. The choice of Tuve was inspired and problematic in equal measure. Tuve was unquestionably brilliant. He'd made significant contributions to experimental physics, particularly in the use of pulsed radio waves, and possessed an intuitive understanding of electronics that his colleagues found remarkable. He was also temperamental, abrasive, and completely intolerant of bureaucratic obstacles. Tuve had a reputation for reducing subordinates to tears with his criticism, and for engaging in screaming matches with military officers who questioned his methods. He was, by multiple accounts, one of the most difficult men anyone involved with wartime research had ever worked with. He was also exactly the person needed to solve an impossible problem under extreme time pressure. In September 1940, the Tizard mission arrived from Britain, bringing with them details of British proximity fuse research, including circuit designs and technical specifications of what they'd attempted. Tuve and his team examined the British work, acknowledged its value, and promptly concluded that the British approach wouldn't work for artillery shells. The British designs were too large, required too much power, and weren't rugged enough. Tuve later said, with characteristic bluntness, that the British had done valuable theoretical work, but, quote, "that was not the one we made to work," end quote. What Section T needed was something that could fit into the nose of a 5-inch shell, leaving room for the high explosive charge. It needed to function on internal battery power. It needed to withstand 20,000 times Earth's gravity during firing. It needed to work reliably in tropical heat and Arctic cold. It needed to have indefinite shelf life so shells could be stored for months. And it needed to be manufacturable in quantities of millions, at a cost that wouldn't bankrupt the government. Every aspect of that specification seemed impossible to someone. The size constraint alone appeared insurmountable. Tuve's solution was to redesign everything from first principles. Rather than trying to miniaturize existing radio components, Section T would design entirely new components specifically for this application. The team included some of the brightest minds in American physics and engineering. Among them was James Van Allen, a young physicist who would later achieve fame for discovering the radiation belts around Earth. In 1942, Van Allen was tasked with developing what Section T called rugged vacuum tubes. Van Allen started with miniature tubes manufactured by Raytheon and Sylvania for hearing aids. These were the smallest vacuum tubes available, about the size of a man's thumb. They were designed for the gentle environment of sitting in someone's pocket, where the most violent shock they might experience would be accidentally dropping the hearing aid on a wooden floor. Van Allen needed tubes that could survive forces 300,000 times more violent. Working with engineers at Sylvania, Van Allen redesigned the tubes component by component. The glass envelopes were thickened using a special composition that was carefully annealed to prevent shattering. The internal filaments and grids, the delicate structures that gave vacuum tubes their function, were shortened and made with heavier cross-sections. Every wire was reinforced, every connection was strengthened. The tubes were then potted in wax inside the Fuze body, which cushioned them against shock. Testing was conducted at the Naval Proving Grounds in Dahlgren, Virginia, using a vertical gun that fired shells straight down into soft earth. The ground caught the shells gently enough that researchers could recover the fuses and examine the tubes under microscopes to see what had broken. Through hundreds of test firings and thousands of design iterations, examining each failure, modifying designs, and testing again, the team gradually developed tubes that could survive. By September 1941, they were achieving success rates above 50%. This was breakthrough progress, but still inadequate for combat use. The Navy, desperate for any improvement in anti-aircraft effectiveness, authorized production tooling anyway, gambling that reliability would improve during manufacturing scale-up. That gamble proved correct. By early 1943, reliability had climbed above 90%. But vacuum tubes were only one challenge among many. The fuse needed electrical power. Conventional batteries were too large and had limited shelf life, particularly in tropical heat, where batteries would deteriorate during storage. Section T engineers developed what they called a reserve battery, using a liquid electrolyte kept separate from the battery plates by physical barriers. When the shell was fired, centrifugal force pushed the electrolyte through channels where it made contact with the plates, generating electricity. This design gave the batteries indefinite shelf life because the chemical reaction didn't begin until the moment of firing. The fuse needed multiple safety mechanisms. It couldn't arm until well clear of the gun to prevent premature detonation that might destroy the firing ship. It required protection against accidental detonation from radio interference or the ship's own radar. When fired at low angles over water, the radio waves could reflect off the ocean surface and trigger premature detonation, so the fuse needed special circuitry to suppress those reflections. Each safety feature added complexity, more components, more potential failure points. By the time development was complete, each proximity fuse contained approximately 130 miniaturized electronic components packed into a steel case, 8 inches long and weighing just over 2 pounds. Inside was perhaps the most sophisticated piece of miniaturized electronics that existed in 1942, a complete radio transmitter operating at roughly 180 to 220 megahertz, a receiver circuit tuned to detect frequency shifts from reflected signals. The reserve battery, arming mechanisms, safety circuits, a detonator, and those 4 precious rugged vacuum tubes that made the entire system possible. On August 12, 1942, the light cruiser USS Cleveland conducted the first operational test in Chesapeake Bay. The target was 3 radio-controlled drone aircraft. Using conventional ammunition, these maneuvering drones typically required dozens of shots to destroy. Cleveland's gunners, firing proximity-fused shells, destroyed all 3 drones with just 4 bursts on the first day of testing. The Navy immediately cancelled the remainder of scheduled tests and ordered mass production to begin. 5 companies were selected to manufacture the fuses: Crosley Corporation in Cincinnati, Radio Corporation of America, Eastman Kodak, General Electric, McQuay Norris. Production started slowly. By the end of 1942, factories were producing 500 fuses per day. Then, American industrial capacity demonstrated why it would prove decisive in the war. By late 1943, production had reached 40,000 fuses per day. Over the course of the war, American industry would produce more than 22 million proximity fuses at a cost exceeding $1 billion 1940s dollars. More than 100 factories participated in some phase of production. The Crosley Corporation in Cincinnati alone produced 5,259,113 fuses, representing 24% of total production. Sylvania Electric Products in Ipswich, Massachusetts, produced even more, manufacturing 5,683,320 fuses, while simultaneously producing 95% of all miniature vacuum tubes used across the entire program. Thousands of workers, many of them women with no previous technical experience, assembled the intricate components under microscopes, working in conditions of absolute secrecy. The security surrounding the proximity fuse was second only to the Manhattan Project. Workers signed secrecy oaths and were searched entering and leaving facilities. They did not know what they were building. The device was given the deliberately misleading code name VT Fuze, supposedly standing for variable time, to disguise its true nature as a radio proximity detector. Even its existence was classified. The very fact that such a weapon had been developed remained secret. Most importantly, use of the fuse in combat was initially restricted to situations where there was virtually no chance of a dud falling into enemy hands. Pentagon officials and Allied commanders understood that if Germany or Japan recovered an intact proximity fuse and reverse-engineered the technology, the strategic balance could shift catastrophically. If Germany equipped its anti-aircraft guns with proximity fuses, intelligence analysts estimated bomber losses could increase by 300%. The Allied strategic bombing campaign, which was already suffering severe casualties, might become impossible to sustain. So the fuses were used only over water, where dud shells would sink beyond enemy reach. When a proximity-fused shell accidentally landed on Sicily during the invasion in July 1943, headquarters dispatched a special patrol to recover it before German forces could find it. This absolute security restriction meant that the weapon remained largely unused in the European theatre throughout 1943 and into early 1944, even as it was proving devastatingly effective in the Pacific. The first combat use came on January 5, 1943, off Guadalcanal in the Solomon Islands. 4 Japanese HED-3A dive bombers attacked a U.S. Navy task force. As the aircraft broke off their attack, the cruiser USS Helena fired 3 salvos of proximity-fused shells at the departing bombers. All 3 shells exploded near one of the aircraft, shredding it with shrapnel. The aircraft plunged into the sea. Helena's gunners had achieved what would have required dozens of conventional shells. Word of the success spread rapidly through the Pacific Fleet. By mid-1943, substantial quantities of proximity-fused ammunition were being shipped to Pearl Harbor. Combat results exceeded every prediction. In 1943, proximity-fused anti-aircraft fire was credited with more than half of all Japanese aircraft downed by naval gunfire, despite proximity fuses being used in only 25% of shells fired. The true effectiveness was demonstrated during the kamikaze campaigns of 1945. On May 11, 1945, off Okinawa, 2 destroyers, USS Hadley and USS Hugh W. Hadley, came under assault from approximately 150 Japanese aircraft during Operation Kikusui No. 6. Many were loaded with explosives and intent on suicide runs. During approximately 1 hour and 25 minutes of intense combat, the 2 destroyers and supporting craft faced overwhelming odds. Hadley's gunners knocked down 23 enemy planes using proximity-fused ammunition before the ship was finally hit by 1 bomb, 3 kamikazes, and 1 Oka rocket bomb. The destroyer was left devastated but still afloat. The after-action report stated that proximity-fused ammunition was indispensable to the ship's survival. Without it, the destroyers would have been overwhelmed in the opening minutes of the attack. But the weapon that would finally force the Pentagon to lift its absolute security restrictions on proximity fuse use over land wasn't Japanese kamikazes. It was a German terror weapon that began falling on London in June 1944, 1 week after D-Day. The V-1 flying bomb, designated Vergeltungswaffe 1, Vengeance Weapon 1, by the Germans, was unlike anything Allied forces had encountered. It wasn't a bomber piloted by a crew. It was an early cruise missile, a pilotless aircraft powered by a simple but effective pulse jet engine that created a distinctive buzzing sound. The British called it the buzz bomb, or doodle bug. To the people of London, it became the sound of terror. At 4:25 in the morning on June 13, 1944, the first V-1 struck London. It landed in Grove Road in Bow, destroying a railway bridge and nearby homes. 6 people were killed, 30 injured, 200 made homeless. Over the next hours and days, more V-2 arrived. By the end of June, hundreds were being launched daily from sites across the English Channel in occupied France. The V-1 was devastatingly effective not because of its explosive power, which was roughly equivalent to 2 conventional aircraft bombs, but because of its psychological impact. The missiles arrived without warning at any hour of day or night. Londoners learned to recognize the distinctive sound of the pulse jet engine, a mechanical buzz that could be heard from miles away. But the true horror came when the engine stopped. The V-1 was designed to run out of fuel over its target area. When the fuel was exhausted, the engine quit, and the missile entered a steep dive. From engine cut-off to impact was approximately 12 seconds. 12 seconds during which everyone who heard the silence knew a ton of high explosive was falling toward them but had no idea where it would strike. A city block, a factory, a hospital, a school, their own street. 12 seconds of silence before the explosion. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Between June and September 1944, Germany launched more than 8,000 V-2 against Britain, with the vast majority aimed at London. The missiles killed over 6,000 civilians and injured 17,000 more. They damaged or destroyed tens of thousands of homes. More than 1 million people evacuated from London, fleeing the random terror of weapons that struck without warning and without mercy. British defences struggled desperately to stop the onslaught. 3 layers of defence were established. Fighter aircraft patrolled over the English Channel, attempting to intercept V-2 before they reached the coast. Some pilots became skilled at flying alongside the V-2 and, using their wingtips to flip the missiles' wings, tumbling the gyroscopes and sending them crashing into the sea. But this required exceptional skill and nerve, and many V-2 were too fast for even the fastest fighters to catch. The second layer was anti-aircraft guns positioned along the southern coast, particularly in Kent. These batteries fired thousands of rounds at incoming V-2 using conventional time-fused ammunition. Their success rate was abysmal. In the first week of operations, anti-aircraft guns destroyed only 17% of V-2 entering the coastal gun belt. Gunners were expending thousands of shells to down each missile. The mathematics were unsustainable. The third layer was barrage balloons deployed around London, cables suspended in the air in hopes that V-2 would strike them and crash. This proved marginally effective but required deploying approximately 2,000 balloons and still allowed most V-2 through. By early July 1944, the situation was desperate. V-2 were arriving at a rate of 100 to 150 per day. Prime Minister Winston Churchill told Parliament that casualties were running at almost exactly 1 person per bomb. The weapon wasn't going to win the war for Germany, but it was inflicting a level of civilian casualties and disruption that threatened British morale and war production. Allied commanders faced an agonizing decision. The proximity fuse could dramatically improve anti-aircraft effectiveness against the V-2. Everyone knew this from test results. But using proximity fuses over land meant accepting the risk that duds would fall into German hands. For more than a year, that risk had been deemed unacceptable. Now, with London under sustained bombardment, the calculation changed. Churchill personally authorised use of proximity fuses against the V-2. Modified fuses were rushed into production, specifically calibrated for the small, fast V-2, which presented a different target profile than manned aircraft. British 3.7-inch anti-aircraft guns and American 90mm guns were equipped with the new ammunition and rushed to positions along the southern coast. The deployment happened with extraordinary speed. On June 15th, just 2 days after the first V-1 attack, Allied commanders were already requesting authorization to use proximity fuses. By late June, limited quantities were being issued to selected batteries for testing. By mid-July, hundreds of anti-aircraft guns along the coast were firing proximity-fused ammunition. The effect was immediate and dramatic. In the first week of operations using conventional ammunition, guns had destroyed 17% of Vone second entering the coastal belt. Within 4 weeks of introducing proximity fuses, that rate climbed to 60%. By August 23rd, it reached 74%. During one day in late August, 82% of incoming Vone second were shot down. The destruction rate had increased by nearly 500%. The transformation was so dramatic that British officials, not privy to the proximity fuse secret, couldn't understand what had changed. One member of a British Home Guard anti-aircraft battery, which had been firing thousands of rounds at Vone second with minimal effect, watched an American 90mm gun crew set up nearby. Over the course of an afternoon, the American battery shot down 4 buzz bombs with 8 shells. When British gunners asked the American battery commander how they'd managed it, he replied facetiously that his crew was made up of Tennessee natives who were all crack shots. The real answer was technology that seemed like science fiction. Each shell was detonating automatically when it sensed a V-1 within approximately 50 feet, regardless of whether the gunner had aimed perfectly. A shell that missed by 30 feet was just as effective as one that missed by 5 feet, as long as it was within detection range. This margin for error meant that gunners no longer needed to predict the exact future position of a target moving at 400 miles per hour. They just needed to get close. General Frederick Pyle, commanding British Anti-Aircraft Command, later wrote in the Times of London that it was the proximity fuse which made possible the 100% successes that Anti-Aircraft Command was obtaining. He credited American scientists with giving Britain the final answer to the flying bomb, but the proximity fuse's peculiar sensitivity created one unexpected problem. The radio detection system was so precise that shells occasionally detonated when passing close to seagulls. British coastal batteries recorded a number of seagull kills, birds that had the misfortune to be flying in the wrong place when anti-aircraft shells passed nearby. This was noted in official reports with a mixture of amusement and concern about ammunition waste. But the sensitivity that could detect a seagull was exactly what made the fuse so effective against the V-1. The success against Vone second meant that the secret was partially compromised. Thousands of fuses were being fired over land. Duds inevitably fell where they could be recovered. The risk that Allied commanders had considered unacceptable for so long was now unavoidable. If proximity fuses were going to be used to defend London, they would eventually be used elsewhere. In September 1944, Allied forces overran most of the V-1 launch sites in France, largely ending the threat to London. But Germany immediately shifted the V-1 campaign to target Antwerp, the crucial Belgian port through which Allied supplies flowed to support the advance into Germany. Between September 1944 and March 1945, Germany launched 2,500 Vone second and V-2 ballistic missiles at Antwerp. When Germany modified the Vone second to fly as low as 1,200 feet, making interception far more difficult, physicists at the Applied Physics Laboratory quickly designed a modified proximity fuse, specifically for low-altitude intercepts. The devices were rushed into production at the Crosley factory in Cincinnati. Churchill authorized a special flight of Lancaster bombers to transport the fuses from Cincinnati directly to Antwerp, demonstrating the weapon's strategic importance. One anti-aircraft battalion in Antwerp destroyed 48 of the first 75 Vone. Second, they engaged using proximity-fused ammunition. The port of Antwerp remained open throughout the German V-weapon campaign, ensuring Allied logistics continued flowing. Without proximity fuses, the V-1 and V-2 attacks might have succeeded in closing the port, potentially delaying the Allied advance by months. By the final months of the V-1 campaign, British anti-aircraft defences equipped with proximity fuses were achieving destruction rates exceeding 90% on some days. The weapon that had terrorised London just months earlier was being systematically annihilated before reaching its targets. Of the approximately 10,500 Vone second launched against Britain during the entire campaign, only about 2,400 reached London. The majority were destroyed by the combined defence system, with proximity-fused anti-aircraft fire accounting for the largest share of kills. The cost of this defense was measured not just in ammunition expended, but in lives saved. Each V-1 that reached London killed on average 2 to 3 civilians and injured several more. Each V-1 destroyed over the Channel or over unpopulated areas represented casualties prevented. Statistical analysis suggests proximity fuses saved thousands of British civilian lives during the summer and autumn of 1944. But the V-1 campaign had forced Allied commanders to accept what they'd resisted for more than a year. Proximity fuses would now be used over land, security restrictions or not. The weapon was simply too effective to withhold. In December 1944, that decision would prove crucial when Germany launched its final desperate offensive in the West. On December 16, 1944, more than 200,000 German troops and nearly 1,000 tanks launched Operation Wacht am Rhein, Hitler's last gamble to split the Allied armies and capture the vital port of Antwerp. The offensive, which would become known as the Battle of the Bulge, took the Allies completely by surprise. Within days, German forces had driven a bulge 50 miles deep into Allied lines. Colonel Oskar Alfred Axelson, commanding the 406th Artillery Group, faced an immediate crisis. German forces were assaulting the 38th Cavalry Squadron near Monschau. The lightly armed cavalry desperately needed artillery support. Axelson had recently received proximity-fused shells, code-named POSIT, but Supreme Commander Dwight Eisenhower had not yet formally authorized their use over land in the European theater. The secrecy restrictions were technically still in place. Axelson decided the emergency trumped restrictions. He ordered his gunners to fire the proximity-fused shells. The effect on German forces was devastating. For the first time in the European theater, American artillery was firing airbursts with perfect consistency regardless of visibility or terrain. Each shell exploded 20 to 50 feet above the ground, precisely calibrated for maximum effect against personnel. The fragments spread in a cone-shaped pattern that covered an area far larger than a ground burst. Foxholes provided no protection. Traditional defensive positions became death traps. The shrapnel rained down from above, penetrating even log-reinforced bunkers. German soldiers who had survived years of combat on the Eastern Front had never experienced anything like it. On December 19th, 3 days into the offensive, Eisenhower formally requested authorization to use proximity fuses without restriction. On December 21st, all limits were lifted. Over the next 6 weeks, 200,000 proximity-fused artillery shells were fired in the European theater. The impact on German forces was immediate and catastrophic. Lieutenant General George Patton later wrote to the War Department describing an action near the Sauer River where his Third Army had caught a German battalion attempting to cross. A concentrated barrage of proximity-fused shells killed 702 enemy soldiers by actual count. Patton wrote that the new shell with the funny fuse was devastating. He predicted that when all armies possessed this weapon, they would need to devise entirely new methods of warfare. German prisoners of war interviewed by American intelligence officers captured the psychological impact. One German artillery officer described the proximity fuse as demonstrating a fundamental difference in industrial capacity. American engineering, he said, solved impossible problems, and through massive application of resources. The proximity fuse required extraordinary manufacturing capacity and acceptance of high costs. Germany could never have produced such a weapon, not because German engineers were less skilled, but because German industry could not support the required infrastructure. Another prisoner, a Luftwaffe engineer, focused on the implications for air defense. If Germany had possessed proximity fuses, he estimated the Allied strategic bombing campaign would have become unsustainable, with loss rates reaching 15 to 20% per mission. But he immediately added that Germany could not have developed it with available resources. The proximity fuse required an economy that could allocate billions of dollars to a single weapon system and mobilize over 100 factories. Only America possessed such capacity. Technical intelligence gathered from captured German documents after the war revealed the full scope of German proximity fuse research. Germany had indeed developed more than 30 different approaches, some remarkably sophisticated. The Kranich acoustic fuse used a mechanical tone filter connected to a resonating reed switch. Rheinmetall Borsig developed an electrostatic fuse using capacitive detection. There were optical fuses, magnetic fuses, and experimental radio fuses similar to the American design, but none had advanced beyond limited testing. When research resumed at Rheinmetall in 1944, hundreds of working prototypes were developed and test-fired. By then, it was far too late. Germany lacked the industrial capacity to establish mass production. Even if production facilities could have been built, the resources required would have competed with production of tanks, aircraft, and basic ammunition. The American proximity fuse program succeeded because it had resources that dwarfed the entire German military research budget. The program consumed over $1 billion 1940s dollars. This included not just research and development, but building dedicated production facilities, training tens of thousands of workers, and maintaining absolute secrecy around the entire program. At peak output, American factories were producing 70,000 fuses per day. That represents nearly 3 billion individual components, manufactured to precise specifications, assembled, tested, and shipped to combat theaters around the world. The cost per fuse fell dramatically as production expanded. In 1942, each fuse cost $732. By 1945, mass production techniques had reduced the cost to just $18 per fuse. This 97.5% cost reduction resulted from manufacturing innovations, increased efficiency, and economies of scale. At $18 per fuse, the weapon was expensive, but not prohibitively so. The increased lethality justified the cost. A proximity-fused shell was worth 5 to 10 conventional shells in terms of target effect. Since the shell itself cost the same regardless of fuse type, paying extra for a fuse that multiplied effectiveness was an obvious value. The secrecy remained absolute until September 1945, when the war ended, and the proximity fuse was finally revealed to the public. For workers who had spent years manufacturing components without understanding their purpose, the revelation was profound. They learned they had built the weapon that had defended London against Vaughan's Second, protected the fleet at Okinawa, and helped break the German offensive in the Ardennes. The proximity fuse demonstrated multiple technological advances that extended far beyond its immediate military application. Miniaturized vacuum tubes required breakthroughs in material science, particularly in glass composition and annealing techniques. The printed circuit boards used in later fuse versions were among the first mass-produced examples of a technology that would revolutionize electronics. The reserve battery design using centrifugal activation was genuinely innovative, but perhaps the most significant advance was in manufacturing and quality control. Producing millions of complex electronic devices with consistent quality required systems and processes that barely existed before the war. American industry developed statistical quality control methods, automated testing procedures, and supply chain management systems that became foundations of modern manufacturing. James Van Allen, the physicist who helped develop the rugged vacuum tubes for proximity fuses, later applied the same miniaturization techniques to scientific instruments for space exploration. The Explorer 1 satellite, launched in 1958, credited with discovering the Van Allen radiation belts, used instruments that drew directly on proximity fuse technology. The knowledge gained from making electronics survive, artillery acceleration, helped make electronics that could survive rocket launches into space. Engineers who had worked on proximity fuses went on to careers throughout the electronics industry, bringing expertise in miniaturization, quality control, and mass production. The intellectual capital developed during the proximity fuse program helped establish American leadership in electronics and technology throughout the second half of the 20th century. Modern weapon systems use descendants of the World War II proximity fuse. The Phoenix missile, the Standard Missile family, and the Patriot surface-to-air missile all employ proximity fuses based on the same fundamental concept developed in 1942. Today's fuses use solid-state electronics, microprocessors, and sophisticated signal processing. They can discriminate between real targets and decoys and operate in jamming environments, But the core principle remains unchanged. Detect the target using radio reflections, calculate the optimal detonation point, and trigger the warhead for maximum effect. The story of the proximity fuse is ultimately a story about what was considered impossible becoming not just possible but routine. Every expert who examined the problem before 1940 concluded it couldn't be done. Vacuum tubes couldn't be made small enough. They couldn't be made rugged enough. The entire system couldn't be manufactured cheaply enough. The technology simply wasn't ready. Merle Tuve and his team at Section T proved every expert wrong. They succeeded not by waiting for technology to advance, but by advancing the technology themselves through systematic engineering, rigorous testing, and relentless iteration. They spent 4 years being told their project was worthless, that they were wasting time and resources on a weapon that would never work. The vindication came in the skies over London in the summer of 1944, when gunners like Sergeant Malcolm Price fired shells that detonated in midair without hitting anything visible and watched V-1 flying bombs fall from the sky. It came in the forests of Belgium in December 1944, when German soldiers realized that their defensive positions provided no protection against shells that exploded overhead with perfect precision. It came in the statistics that showed proximity fuses increasing anti-aircraft effectiveness by 5 to 10-fold, turning weapons that had been marginally effective into decisive defensive systems. And it came in the lives saved, the ships that weren't sunk, the cities that weren't destroyed, the campaigns that succeeded because air defense actually worked for the first time in history. Churchill called the proximity fuse potent. Patton called it the weapon that won the Battle of the Bulge. Vannevar Bush credited it with 3 war-winning effects: defeating kamikaze attacks in the Pacific, neutralizing German V-1 attacks on England, and revolutionizing land warfare in Europe. The proximity fuse stands as testament to what can be achieved when brilliant minds are given impossible problems, unlimited determination, and the industrial resources to turn theory into reality. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.